Okay, we're going to go ahead and get started. This shouldn't take too long, hopefully 30 minutes or so. For the most part, these Zoom meetings won't take the entire lab period because mostly I'm just going to be going over some of the background stuff, sort of like the talk I would usually give at the beginning of the lab anyway. Um, the way this is going to work is ideally we're going to meet every week. Now, we won't meet next week because of Labor Day. Um, right now, the plan is that the week after that, we will meet in lab, but we'll let you know for sure what's going on with all of that. We're going to try to go through the labs in order. We'll see how that goes. I will let you know if we're going to do things out of order. So as far as preparing, just assume that we're going to go through the manual in order the labs are in. So generally, what I'd like you to do is have read through the lab. I'm not expecting you to have done that necessarily this time, but read the lab before our Zoom meeting. I'll go over the background and sort of what's expected of you to do for that lab. And then you will have 1 week to turn in whatever the assignment is. So your assignment will be due before the next lab starts. There'll be a place to turn it in on Canvas. Make sure you do that. Because we're all one big Canvas group, essentially how the class is set up, the due dates won't necessarily reflect your exact due date. So just remember, your assignment is due before the next lab would start. So because we're meeting on Monday and next Monday is Labor Day, you will all have a little bit of extra time. I'm not going to make the lab due on Monday, so it'll actually be due on Tuesday, and that's really only going to matter for these Monday labs. Everyone else will have just the normal week to do it. But so for this first lab, the assignment will be due by 3:30 on Tuesday of next week. And there'll be a spot to upload that on Canvas. So to start with, I'm going to go over some of the things that you'll need for the reports, just some of the stuff about the reports in general. I'm going to show you the resources we have. So we've got some videos you can watch, one that shows the actual lab being performed, one that's me going through all the equations, and I'm going to talk a little bit about that right now anyway. And we've got some PowerPoints, and I'm going to show you those. All that stuff is on Canvas. So to start with, I'm going to talk about the measurements lab, the lab reports that you'll have to do for, you won't have a report for every lab, but you will for this first one. And the way we try to do it is essentially you'll have a report to write every other week. And that gives us an opportunity to grade reports, so you're never writing another report without having gotten feedback on the previous one that you read or that you wrote. If you have any questions, you can go ahead and ask me in the Zoom chat. I'll try to keep an eye out for them. Otherwise, I'll go ahead and get started. And so we've got a few things on Canvas for you to look at. I'll show you these two things in just a second after I talk about these a little bit. My name is Justin Van Cleve. This is my email. It's in this PowerPoint that's on Canvas. If you have any questions throughout the week, if you aren't sure how to do something, if you aren't sure you're doing something right, send me an email. So don't bother the other TAs. They're in this thing to look at, but for any of the lab related stuff, ask me. Okay, so I talked about this a little bit. Due dates are essentially, for the most part, assume that they'll be due a week after the assignment. So a week after the lab. I will let you know otherwise. For reports, you must submit them as a PDF. So, and that's because if you upload it as a .doc or a .docx file or whatever, a lot of times it'll show up weird in Canvas when I open it. And if stuff is formatted wrong or things like tables or figures don't show up, you will lose points, and that's just how it goes. So make sure you upload it as a PDF. Make sure none of that stuff happens, and you can do that from Word. Okay, so some basic stuff on writing, third person, passive voice, past tense. So never use first person. Make sure you're always using past tense. So things like the measurement was taken is how you want to word things, not we took the measurement, not we will take the measurement, not not will be taken, are taken. So that's like present tense. So that's not as far as the passive voice stuff. I'm not going to be super hard on you on it. I will point it out, and you'll probably lose something like a point. But things like past tense, things like trying to use first person, those will be worth more points. Those are more obvious things. Make sure you don't do that. You never want to do that in technical writing. Okay, so sections that are going to be in the lab, and I'll go ahead and show you this template that we have. So this is on Canvas. You're going to want to write the reports exactly like they show up on here, and you can take, this is a Word file. If you're doing it in Word, you can open this up and just directly copy over the things. So you'll have a title page, but the title of the lab, your name, the date will be the date that it's due. The lab section needs to be your actual section. So I think you are all section 10. So the sections will actually go in the lab. You'll have an objective section, a background section, procedure, results, conclusions, and then references and an appendix if you need it. For the most part, you won't need an appendix, but there are different things you can do. So you'll have to do sample calculations, and I'll talk about that in a minute. And if you want to, you can put sample calculations in an appendix, or you can show them as you do them in the lab. But these are all the sections that we'll be looking for. So follow this format. I want you to follow it exactly. Same font size, same margins, all that kind of stuff. We want all the lab reports to look the same formatting wise. So yeah, title page, objective, background, procedure, results, conclusions, references. And we have a rubric as well. I think I closed it. Let me open that back up. Oh, I have that. Okay. Yeah, here's the rubric. Okay, so the rubric is how we're going to go about grading the reports. So make sure you look through this and do all of the things that it asks for, or we try to be fairly specific in how we outline things. General ideas for some of this stuff. So the background and the procedure, someone who doesn't know anything about the lab should be able to read those two sections and recreate the experiment. That's the idea behind them. So in the procedure, make sure you give some detail. Don't rewrite it exactly as it shows up in there. So make sure you're using your own words. I understand that you're not actually going to be doing the experiment, so it might be a little bit harder, but we have a fairly clear procedure in the manual. Try to rewrite that. Try to give enough detail that someone could recreate that experiment. So this rubric file is on Canvas. Make sure you're looking through this as you're doing the report, because this is how we will grade it. This is what we're going to be looking at when we grade your reports. Okay, yeah, so title page. Make sure you're putting your actual section. Again, I think you are all section 10. And the date is the due date, not the date that you write it. So what's the objective of the lab? That'll be a couple of sentences. The background, you're going to talk about any theory stuff that's important for that lab. So, and I'm going to go through this in just a minute, but for the first report, it's going to be all of the like dimensional analysis stuff, essentially, and some description of how the experiment apparatus works, what it is, um, a figure if you need it. So yeah, procedure, give enough detail that someone else could replicate the experiment. Shouldn't have any, no results, no equations in there. It should be just the steps that are required to perform the experiment. You make sure you're doing that, again, passive voice, past tense, not in first person. So it's very typical because the manual is written as like steps in present tense. A lot of people will end up writing the procedure like it's directions for someone to follow directly, and you want to talk about what was done, not as like present tense steps, like you'll see in like in a lab manual. So results should be all your tables, all your figures, your calculations, whatever the thing you're trying to calculate for that lab is, should be in there. So you'll have to do sample calculations. So for this first lab, I think I'll talk about that a little bit more when we get more into this specific lab, but we'll be looking for pi 1, pi 2, pi 3. I think it's rho b and ds, so bulk density and spherical diameter, the things that we're looking for sample calculations of. But so this is an example of a sample calculation. So it's the thing you're doing a sample calculation for. It written out just symbolically. Numbers plugged in, and then what the answer is. So you need to do one of those for each thing that we're looking for a sample calculation for. And the general idea of sample calculations is it's for anything that you show in a table that you calculated. You need to show a sample of how you got that number. We will tell you what things we're looking for sample calculations for. And again, it'll just be one for each of the things. So you don't need to show one sample for every calculation of that specific number that you did, but for every general one, you need a single sample calculation. So tables and figures, every report you're going to have tables and figures in. You're either going to have the recorded data, like the raw data from the lab. You're going to have figures generally for everyone. You're going to have to plot something. So you have to have a number with it. For tables, it'll be like a title for the table. For figures, it'll be in a caption that goes below the figure. So you must introduce them in text before you show it. So the easiest way to do that is in a paragraph just before, but somewhere in writing, you need to have talked about that table or figure before you show it. We want 3 significant figures for everything. So for figures, you need title, axis label. If we ask for a trend line, put a trend line on there. If there's a trend line, you need the equation. And if there's a trend line, you need the r-squared value. So as an example, so a title, we got our axes labeled. We got the trend line equation and the r-squared value. We've talked about it somewhere in a paragraph before that. And we've got a caption with the figure number. So the title, it's fine if you use symbols. In the caption, it needs to be some sort of description of what the figure is. So the R squared is how good the trend line is. So it's an evaluation of whether that was an appropriate type of fit equation to use for the data set. That's why you need to show it with it. Okay, so the conclusions will be sort of different for whatever the lab is. When I go through this lab, I'll talk a little bit about what exactly we're going to be looking for as far as what the conclusions of the experiment are. But you need to, whatever we tell you we're looking for, you need to make sure you actually discuss that in your conclusions. So you need to comment on how good those results are, whether they make sense or not. And you also need to do some sort of error discussion about possible error sources in the conclusion section. So for references, so part of this is just to have a references section and to get you into the habit of understanding how to write a reference. So for every lab, you have to write, you have to do a reference for the lab manual. So if you use any other sources, make sure you reference those. You will lose a lot of points if you take info from some other third party and don't reference it, because that's essentially plagiarism. So make sure if you're using any other things, you reference them. All right, we're back. This should, I'm recording this and I'm gonna post that video at the end, and I'll send out a link to it. It'll end up on YouTube, and I'll send you a direct link to everyone or as an announcement on Canvas. Okay. So that's all the basic stuff for the lab reports. Make sure you give yourself time to do these, especially the first one is going to take you longer than you think it will. Don't wait until the last minute to do it, because you're not going to get it done. So yeah, give yourself time, especially this first one is going to take you some time, so get started on it early. Okay, so the dimensional analysis lab. So I've got a little PowerPoint here. Again, this is on Canvas for you to look through. So I'm just going to go through it really quick. Then I'm going to go through the lab manual a little bit, and then I'm going to show you where we have links to things, and that'll be it. So this first lab, this dimensional analysis lab, is looking at granular flow. So we have some granular material, and we're storing it in a vertical column, and we're letting it flow out. And we want to know what the mass flow rate is. So this is useful for a lot of different industries. So you have things like, imagine like grain storage, like if you have like corn or ground wheat or something in a silo, and you want to have, keep track of what the mass flow out of it is, and you're filling things. Or for making like pharmaceuticals, when you're trying to add materials into like a pill making machine, or for like nuclear charge. So there are a few different things where this idea of granular flow is useful, and it poses some extra challenges because granular materials are multi-phase. So you've got the actual material, and then you've got air all around it. So it's a little bit harder to model what the flow rate is going to be. So what we're doing in this lab is we're going to use dimensional analysis to reduce the number of parameters and then come up with a sort of simplified experiment that we can run where we can compare two different parameters that we think are going to have the most impact on the flow rate and find out through the experiment which one of those affects that mass flow rate more. So the Buckingham Pi theorem, dimensional analysis, you probably saw, if you remember, in fluids, you worked with this. So it's a way of non-dimensionalizing things. So you can run an experiment and then sort of extrapolate from that to different sizes of things. So in this lab, the grounded material are like plastic beads, acrylic pellets. They're like what you would use in like an injection molding machine. So they're just plastic beads. So an important thing to know is we're assuming that they're spherical for ease of calculations, but the actual grains are really like little cylinders. And so we have measured a bunch of them as far as the long distance and the short distance, so they're cylinders. So we've measured like how high they are and like the diameter of them. And we've averaged those, and that's what the spherical diameter number that we'll give you is. And so we're going to give you all of the raw data from this lab, and that's what you'll actually use for writing the report and doing the calculations. So this is what the experiment apparatus looks like. So there is a video on Canvas, and I'll show you that at the end really quick. I won't go through the video, but I'll show you. It's posted on Canvas. You can watch it. It's of Brian and I doing one run of the experiment. Basically, so you fill this up to a certain height, you put a plate down that has a hole in it, you measure how long it takes for the material to flow out, and then you weigh it. So you get a mass flow rate, and you know what all the other parameters of the system are. Okay, so bulk density versus like true density. So if you have like liquid, it fills the space. But if you have granular material, it packs together differently, different times. So you have space in between the grains. So you've got a bulk density. So we've also gone in and we've done bulk density measurements. We did 5 of them. And then we're giving you an average of what that bulk density is. So that'll be in part of the data, the raw data that you'll get for this lab. So for this lab report, and I will go ahead and go through the dimensional analysis stuff, and then I'll talk about exactly what the procedure is as far as what you're going to do with this raw data and what we're looking for at the end of the lab. So we have our columns that we're filling up with granular material, and we're trying to find what the mass flow rate is. So the first step in determining how to make an experiment is we want to list all the parameters that we think are going to affect that mass flow rate. So we have the diameter of the vessel. We have the hydraulic diameter of the orifice we're letting the material flow out of. So hydraulic diameter is 4 times the area over the perimeter. So it's not just the diameter. So we have H, which is how high in the cylinder we're filling up with material. We have the spherical diameter of the particles. We have true density and bulk density. So how the density of each individual particle, and then their bulk density, what their density is, and they're all packed together. So we have gravity, which is the main force driving the flow. And then we have some extra parameter for the shape of the orifice that we're letting them flow out of. So when we look at all of these parameters, what we're really saying is we think that mass flow is some function of all of those different things. And all of those different things is too complicated to do an experiment on because there's too many variables here. So we want to use dimensional analysis to reduce the number of variables to something we can work with. Now it's important to note that we're leaving some things out here. This isn't every parameter that could affect the flow. We're not considering friction at all. We're not considering friction between the particles and the edge of the container. We're not considering friction between each particle and each other. We're not looking at things like static forces, which we're using a lot of plastics, and you can generate a lot of static electricity that way. So there's lots of things that we're leaving out here. So that's important to remember, especially when you're thinking about error sources. And this, we're not actually considering every parameter that could affect. So humidity, the wall roughness, lots of different things that we're neglecting. But so what we're saying is that this mass flow rate of this granular material is some function of all those parameters. So we've listed all the parameters. So if we list all of these parameters in terms of the dimensions that they need, so not the units, because we don't want to do anything in any specific units. We want to think about the dimensions. So like mass flow rate is mass per time. So the diameter of the vessel is a length. The hydraulic diameter is a length. The height is a length. The spherical diameter is a length. The density is a mass per length cubed. Bulk density, mass per length cubed. Gravity is length per time squared. It's an acceleration. And the shape factor is just dimensionless. So to represent all of these parameters that we're considering, we need 3 dimensions. And so those are the primary dimensions. That's what we call them. So we need mass, length, and time to represent all of these. So we have the primary dimensions that we need. Now we need to pick some repeating parameters. So the repeating parameters are what we're going to use to make all of our dimensionless groups. So it's really important how we choose repeating parameters. So repeating parameters all of the repeating parameters will end up in every dimensionless group. So they need to be values that we know well, that aren't going to change between runs, and yeah, so they need to be things that we have a good understanding of. So for this lab, we're choosing bulk density, spherical diameter, and gravity. So we're making some assumptions here when we do this. So again, we're saying that these things are going to be constant or easy to control so that we know exactly what these values are going to be. So we're saying that the bulk density doesn't change. That means that we're assuming that this granular material is going to pack in the same way every time. So we're saying that the spherical diameter doesn't change. So we're saying that all these grains are the same size. And we're saying that gravity doesn't change. So gravity is going to be constant. It's not really going to change we aren't doing the experiment in lots of different places. The cylinder isn't miles high. The gravity will be constant over the experiment. So that's a good assumption. These other two may or may not be good assumptions that they're going to be constants. So making dimensionless groups. So the way you make a dimensionless group is we take our 3 repeating parameters and we raise them to arbitrary exponents. Let me see, can I zoom? Yeah. So we raise them to these arbitrary exponents, A, B, and C, and then we multiply them by the thing we're trying to make a dimensionless group for. So the first one of those is going to be our mass flow rate, because that's the thing that we're trying to find. So we have our 3 repeating parameters raised to arbitrary exponents, the thing we're trying to find a dimensionless group for. So now we write them in terms of their dimensions. So we have mass per length cubed to the A, length to the B, length per time squared to the C, and then mass over time. And what we want to do is we want to find what A, B, and C need to be so that we end up with a dimensionless group. So we end up with m to the 0, l to the 0, t to the 0. So we can do that by writing 3 simultaneous equations. So for m, we want it to be 0, so we have 0 equals, and then we have just a, because there's just m here. There's no m in the b term, there's no m in the c term, and there's m to the 1 in the m dot. So we end up with a plus 1 equals 0. So we can go ahead and solve for a. We know that a has to be negative 1. We can do the same thing for length. So we have minus 3a because the L cubed is on the bottom here. We have a B because that's just L. And then we have a C because that's just L. And then we have no length term in that. And then the last one, we have time. We have no time, no time. We have t to the negative 2 in there. And we have t to the negative 1 in there. So we have minus 2c minus 1. So we've already solved for a. We can solve for c with this equation. We get minus a half. And then we can plug a and c into this equation and solve for b, and we get minus 5 halves. And then I don't think I mentioned it, so but choosing the repeating parameters, the other thing is at least each of the primary dimensions needs to show up at least once amongst these 3, and that's so we can end up with these dimensionless groups. Okay, so we plug our A, B, and C in here, and that gives us a dimensionless group. So we have A to the minus 1, B to the minus 5 halves, C to the minus 1 half. And that gives us a dimensionless group for the mass flow rate. So this is a dimensionless mass flow rate. And we'd follow that same procedure going through each of the other parameters that we aren't using as repeating parameters. So we could make a dimensionless packing height. We can make a dimensionless orifice diameter. We can make a dimensionless cylinder diameter. We can make a dimensionless density, and then shape factor is just dimensionless on its own still. So now we've gone from mass flow rate is some function of all these parameters to saying that pi 1 is some function of these other 5 dimensionless groups. So now we're a little bit closer to having something. We've removed some of the parameters. We're a little bit closer to having something we can do an equation with. So remember that when we chose these repeating parameters, we made some assumptions. So we assumed that the bulk density is always going to be the same, and we assumed that the particles were all going to be the same size. So really, if all the particles are the same size and they always weigh the same in bulk, their density must be constant. So we've sort of, just in how we chose our parameters, our repeating parameters, we've assumed this pi 5 is going to be a constant. So then looking at these other things that we have packing height, we have the size of the orifice we're going to let it flow out of, we have the cylinder diameter, and we have the shape of the orifice. So of those, we can make another assumption and say probably the 2 things that are going to affect the mass flow rate the most out of these is going to be how high we fill the cylinder and how large of a hole we let it flow out of. Because gravity is what's causing it to flow. So if we raise the particles, we have more force pushing down. And if we let them flow out of a different size hole, we're letting more flow at a time. So we're going to keep these constant. So we're going to use just one cylinder diameter. We're only going to use one shape. And we've really already assumed that this is constant in how we set up the thing. So now we're saying that our dimensionless mass flow rate is some function of our dimensionless packing height, our dimensionless orifice diameter, and then a constant that is all three of these just combined together, because they're going to stay a constant value throughout the experiment. So now we can go in and we can assume some shape for this function. So what do we think this function is going to look like? And we're going to choose a power function for that, power series. So this is the equation that we come up with, and this is how we define our experiment. So we're saying that our dimensionless mass flow rate is C, our dimensionless packing height raised to some exponent, our dimensionless orifice diameter raised to some exponent. And the conclusions that we want you to come to, so we want you to figure out what affects the mass flow rate more. Is it the packing height or is it the orifice diameter? And you're going to do that based on what these exponents are. So whichever of these has a larger exponent, a change in that value will affect pi1 more than the same amount of change to the other value. So depending on which of these is larger, that's how we want you to determine, that's how you want you to come to the conclusion that that particular parameter is what affects our mass flow rate the most. So we do that by having two experiments. So we do one experiment where we fill the cylinder up to the same height every time. So we have a constant height that we fill the experiment to. So that means our dimensionless packing height is a constant. And then we go through every orifice size we have. So there are 6 different orifices we have. And we record the mass flow rate. And then we do another experiment where we use just one orifice size and we fill the cylinder up to different heights every time. So those are the 2 experiments that we did. And we're going to give you these raw data tables of how that came out. So then what you're going to do is you're going to make plots. So you're going to plot in one the dimensionless mass flow rate on your vertical axis against your change in or your dimensionless orifice size. So you're going to have a bunch of different orifice sizes on your x-axis. You'll have the different flow rates they corresponded to. And then your height will be some constant in that. And then in the other one, you're going to plot, again, your mass flow rate, your dimensionless mass flow rate, but this time it'll be plotted against your dimensionless packing height. So you'll have pi1 versus pi2 in that plot. And for each of those, you'll apply a power fit. And the power fit will give you the exponent. So the pi1 versus pi3 plot will give you this n3 value. The pi1 versus pi2 plot will give you the n2 value. And then you've got to use a combination of the constants you get with that power fit that you apply in order to get the overall constant C. So your results are going to be these tables. And I think what we gave you is like the raw numbers, and you have to calculate like pi1, pi3, but we give you like the time and the mass and the height and the diameters, but you have to calculate these other values. So make sure you give us these full tables. I don't remember exactly what we gave you. We gave you enough to find everything. You're going to need the plots of pi1 versus pi2 and pi1 versus pi3. And then your conclusions are going to be what affects pi1 more. So what affects the mass flow rate more? Is it how high you fill the cylinder or how large of an orifice you let the particles flow out of? So that's in general, what I have for this week, if we want to look, so if you go onto the Canvas page under modules, the manual's there, that PowerPoint that I went through at the beginning on the lab reports is there, the template for lab reports is there, that granular flow PowerPoint, the raw data from the lab, the rubric, and then there is a video of us performing the experiment, and there's also a video of me going a little bit more in detail through the dimensional analysis process. So watch those videos. I also have recorded this Zoom meeting. I will post that under the labs here, and I'll send you an announcement with a link to it. Otherwise, send me an email if you have any questions about what you need to do. So the lab report, again, will be due next week. I'm giving you an extra day because of Labor Day. So for you, it will be due at 3:30 on Tuesday of next week. So turn it in on Canvas before then as a PDF. If you have any trouble when you're writing the lab, don't hesitate to send me an email. I'll happy to answer any questions you have. I'm not gonna like pre-grade your assignment and tell you if you're doing anything wrong, but if you have any questions about what you need to do, or if your answers are reasonable or not, you can ask me that kind of stuff. So are there any questions right now? If you want to, you can type in chat. Let's see, it should. No, it's not published yet. Okay. Oh, no, it publishes all of them. Never mind. I don't want to do that. They should be, if you go to modules, it should be all the way down at the bottom. It's the last thing. Someone want to double check and make sure that that stuff is there? I don't have to unpublish all these other ones. So it should be down at the bottom under modules. So make sure they're there and let me know in the chat if they're not. So yeah, so if you go to modules, there's no labs showing up here. Well, I'll look around in Canvas and make sure. I'll have to see exactly why they aren't showing up yet, because they should be, because they're published. So you should be able to see them. But also, I'll figure out what that is when I get this this video for this Zoom meeting put up.